Okay, we've all seen the periodic table, right? That big, colorful chart that's pretty much on the wall of every science classroom ever. But it is so much more than just a list of elements. It's really a map of the universe's building blocks, and it's a story of some incredible scientific detective work. It's like a secret code that, once you crack it, explains, well, pretty much everything. So, how did one guy manage to basically predict the future of chemistry? Let's dive in. So, our story kicks off with something that honestly sounds a bit like a magic trick. We're going back to 1869, and a Russian chemist named Dmitri Mendeleev is just wrestling with the total chaos of the known elements. But while he was trying to organize them, he did something absolutely extraordinary. He described in vivid detail elements that no one had ever even seen. I mean, that's like describing a person you've never met, down to their personality. So, how on earth did he do it?
To figure that out, we really need to step into his shoes for a minute. For Mendeleev, this wasn't just about making a neat little list. This was about solving a grand puzzle. It was about cracking the fundamental code of the universe itself. Okay, so Mendeleev's genius was really in how he juggled two big ideas at once. First, he started ordering the elements by their atomic mass, lining them up from lightest to heaviest. But at the same time, he was grouping them by their chemical personalities, how they behaved and reacted. And whenever an element popped up that acted just like one he'd already placed, he'd start a brand new row. What this did was create these columns of, well, chemical families. And he was so sure of this pattern that he boldly left gaps in his table for elements he was certain had to exist, but just hadn't been found yet.
But here's where it gets really fascinating. His system, it wasn't perfect. To get those chemical families to line up just right, sometimes he had to break his own number one rule. He would actually swap elements, completely ignoring their mass. This was a huge clue that he was onto a pattern governed by some deeper truth he couldn't quite see yet. The most famous example of this is the whole tellurium and iodine problem. Now, based purely on mass, iodine should come first, no question. But Mendeleev knew that iodine behaved just like chlorine and bromine, so he trusted his gut, his chemical intuition, and he swapped them. He put tellurium before iodine just to make the families line up. And it worked, but it created this nagging scientific puzzle. Why did it work?
And that puzzle? Well, it would bother scientists for decades. Turns out the answer wasn't going to be found by looking at the elements as a whole. No, they had to go deeper, diving right inside the atom itself to find a new, more fundamental way to bring order to the whole table. The big breakthrough came with the discovery of subatomic particles, and scientists realized that the true defining feature of an element wasn't its weight at all, but something way more fundamental, its atomic number. This is just a simple count of the positively charged protons in its nucleus. Hydrogen always has one. Helium always has two. It's a completely unchangeable atomic fingerprint. And that, right there, was the game changer. We went from Mendeleev's table, which was ordered by mass, to the modern table we use today, ordered by atomic number. And with that one simple change, poof, all the inconsistencies, all the little cheats in the original design, they just vanished. So let's go back to our tellurium and iodine mystery. This table just lays it all out perfectly. Tellurium is atomic number 52. Iodine is 53. When you order them by this number, not only do they fall into the correct sequence, but they also land in the perfect chemical families, exactly where Mendeleev's intuition told him they belonged all along. The mystery was finally solved. But, this just raises an even deeper question. Why? Why does ordering by protons create these perfect repeating patterns of behavior? Well, the answer, it turns out, isn't in the nucleus at all. It's in that cloud of electrons orbiting around it. You see, for every proton in a neutral atom, there's one electron. But these electrons aren't just flying around in a random cloud. They're actually arranged in specific energy levels, or what we call shells. And this very specific arrangement is called the electronic configuration. And that is the secret code that determines exactly how an element is going to behave. Now, the rules for filling up these shells are actually pretty simple and orderly. Electrons always fill the innermost shell first before they move outward. So, as you can see, the first shell holds a maximum of 2 electrons, the second one holds 8, and the third also holds up to 8. This layered structure is the key to, well, everything. Okay, let's try to decode an element together. Let's take sodium, atomic number 11. That means it has 11 protons, so it also has 11 electrons that we need to arrange.
So the first shell takes 2 electrons. Okay, 9 left. The second shell takes the next 8. That's 10 electrons we've used up. So that final 11th electron, it has to go into the third shell all by itself. So sodium's unique code is 2.8.1. So this electron code, this 2.8.1, isn't just a random string of numbers. It's actually a set of coordinates. It tells you exactly where to find sodium on the periodic table's grid. It's wild. Let's connect this right back to sodium's code, 2.8.1. The number of shells that have electrons in them, in this case 3, that tells you the row, or the period. So sodium is in period 3. Now the number of electrons in the outermost shell, just 1, that tells you the column, or the group. So sodium is in group 1. The code is literally a map to the element's address on the table. And here it is, maybe the most important takeaway of all. Why do elements in the same group act so alike? It's because when atoms react, it's only their outermost electrons that do the interacting. The inner electrons are all shielded. So an atom's entire chemical personality is almost completely defined by how many electrons are in its outer shell. Just look at the other elements in group 1. Lithium's code is 2.1. We already know sodium's is 2.8.1. Potassium's is 2.8.8.1. Do you see the pattern? It doesn't matter how many inner shells they have, they all end with that same single lonely electron in their outer shell, and that is what makes them a chemical family. It's why they all react in very similar and very vigorous ways. So we've really come full circle, haven't we? We went from Mendeleev's brilliant but flawed attempt to organize elements by mass all the way to our modern understanding that the table is a perfect reflection of atomic structure. The periods, the groups, the repeating properties, it all comes down to the beautifully logical way that electrons arrange themselves in these shells. Which leaves us with one last kind of provocative thought. We know that an element's properties are all dictated by those outer electrons. So, what does an atom do when its most important shell is incomplete? What happens when it has one extra electron to give away, or maybe it's just one electron short of a full set? Well, my friends, that is where all of chemistry really begins.